Merci pour l'invitation. Bonjour. So what I wanted to talk about a bit today, so as Professor Chazelle made clear in his lecture, for the past 10 or 15 years, there's been a very rich interplay between computer science on the one hand, economics and game theory on the other. And so today I just wanted to give you a taste, a glimpse of one facet, one dimension of that interplay. It concerns equilibria, like Nash equilibria that Professor Chazelle discussed, and their inefficiency, the sense in which they are not optimal for society. And you learn this very early on, even if you see only one lecture in game theory, you learn this lesson. You learn it from the prisoner's dilemma, where individual self-interest does not lead to a socially optimal outcome. You learn it once again in the tragedy of the commons. There's been an interesting counterpoint, though, to this ubiquitous inefficiency that's emerged from the computer science community, which is in many interesting application domains. It turns out while self-interested behavior is not completely optimal, you can nevertheless, in certain cases, interesting cases, prove guarantees on proximity to optimality. You can guarantee that self-interested behavior does almost as well as if there was hypothetically an altruistic dictator picking actions for everybody on behalf of society. So many researchers have proven results along these lines now in many different domains. I'm just going to show you one application close to my heart, one about routing traffic through networks. And definitely, please, I invite you to interrupt if there are questions en français, si vous voulez. Thanks. So I'm not going to assume you've ever seen any of these concepts before, so I'm going to discuss mostly what I call first-generation results about the so-called price of anarchy. So this will be basic examples, just a few basic results. Time permitting, I'll discuss the research frontier a bit at the end, what people have been doing over the past few years. So, but for starters, I want to go back even further than just 10 or 15 years ago. I want to go all the way back to 1920 to a book called The Economics of Welfare, written by A.C. Pigou. And at some point in his book, he tells a story meant to illustrate what we would now call a congestion externality. It was an example with traffic on roads, which shows how individual rationality does not lead to something which is the best for everybody. And so what he talks about is a number of drivers in their cars, all leaving a given origin at roughly the same time, and all bound for exactly the same destination. And to illustrate the point, we need to have two different routes, parallel routes, that have different characteristics, one which is sensitive to congestion and one which is not. So just to make the contrast very stark, let's have one route whereby c of x equal 1, what I mean is that the time it takes you as a driver to get from S to T on the bottom route is always 1 hour. It doesn't matter what other people do. So think of it as a highway with an infinite number of lanes. On the other hand, on the top route, if nobody's using it, then you get to T instantaneously, but it takes longer and longer the more people you have to share the route with. So let's say that there's 1 unit of traffic overall, and let's say that if an x percentage, an x fraction of the traffic uses the top edge, it takes an x fraction of an hour. So if half of the traffic uses the top route, it takes 30 minutes. If 100% of the traffic takes the top route, it takes all of them an hour to get from S to T. And so I want to now do a thought experiment, which will eventually culminate in this idea of the price of anarchy, asking, first of all, what would individual people do? These drivers are autonomous. They can pick whichever route they want. Let's assume they want to get there as quickly as possible, so they want the minimum travel time. On the other hand, what would we want for society? What would be optimal? And we'll see how those two outcomes compare. So first of all, what would you do if you were one of the drivers? Well, the choice is clear. It is clear in the sense that Professor Chazelle talked about dominant strategies, actions which are optimal no matter what other people do. So as a driver, it is in some sense a foolproof or brain-dead strategy to always drive along the top route. The reason being is, well, what is the worst possible scenario if you drive on the top? In the worst case, it takes you an hour. What is the best possible scenario on the bottom link? Well, it's never going to be shorter than an hour. So in the equilibrium, or under individual choices by all of the drivers, you would expect not any positive epsilon. You would not expect any split, because if there's a positive epsilon, those in the bottom would regret it and want to switch to the top. But rather, you would expect epsilon to be 0. You would expect 100% of the traffic to be doing the obvious thing, to be driving on the top route, resulting in everybody getting from S to T after an hour's time. Okay? So that's question one. If we let people do whatever we want, whatever they want, what do we expect? What is the equilibrium? So the equilibrium has everybody traveling an hour. The second question is, what, just hypothetically, we could actually choose routes for people. What if we were a dictator and we wanted to implement the outcome best for society? Could we do better? Well, if you think about this example a little bit, you realize anything would be better than this. So for concreteness, let's think about the solution where we force the traffic to split half-half. Okay? Now, this half of the traffic that we've forced to take the bottom routes, they're no better off than before, nor are they worse off. It still takes them an hour to get from S to T. But what we've accomplished is we've now given half of the traffic a relatively uncongested ride along the top route. They get there in only 30 minutes. Okay? So on the one hand, we have a Pareto dominant solution. We've made no one worse off, but some people better off. If I wanted to aggregate everybody's experience, I could look at the average travel time, and that's dropped from 60 minutes to only 45 minutes. So those are senses in which this outcome is better than the previous one. So that's Pigou's example from 1920. I want to show you another example, which illustrates that point, but also some other interesting points. This is from 1968. This is called Brace's paradox. We begin with an unremarkable network. Okay? So it's a little bit more complicated, but not in an interesting way. Now there are two parallel routes. Each has two roads. Each has one road with infinite lanes, and then a second road that is one of these X's, one of the short roads as before. So if we perform the same thought experiment, we don't discover anything very interesting. If we say, well, what will drivers do? Well, because the two routes are exactly symmetric, there's no reason to prefer one over the other. We expect them to split themselves 50-50 between S and T. Half of them will take the top path, half of them will take the bottom path, and everybody will take an hour and a half to get from S to T. If we ask, what would an altruistic dictator do? There's no reason to do anything different than this solution. The two experiments coincide. That's all there is. So why is it called a paradox? The paradox enters when we envision, someone, say the government, trying to build new infrastructure to make the commute time, perhaps between the suburbs and Paris, a little bit faster. Again, to make the point as stark as possible, let's go ahead and assume that this new technology is a teleportation device. It's something which, upon reaching the midpoint of the, can you see that? Oh, I see. So this is a link, an arc here, if you can see that. So what it allows you to do is, when you drive to the midpoint of the top route, you get to travel instantaneously down to the midpoint of the bottom route, if you want. So what happens? So let's repeat the two thought experiments. So first of all, with self-interested drivers, the first observation is they will not continue to do what they have been doing already. They've been doing this red traffic pattern. They've been taking an hour and a half to get to work. And everybody wants to make use of the new technology, of the new teleporter. Right? So if I am a driver and I switch to the zigzag path and nobody else switches, then it takes me only a half an hour plus 0 plus a half an hour, 60 minutes. Better than the 90 it was taking me before. The fallacy in this reasoning, of course, is that I am not the only person who will switch to using the zigzag path. Everybody will reason like I do, and as a result, we get this green routing of the traffic. This means 100% everybody takes the zigzag path. Okay? What is the consequence? Well, now 100% of the traffic takes this length, so that takes an hour. 100% takes this length, so that's another hour, so it takes 2 hours. And again, this is a dominant strategy in the sense that Professor Chazelle talked about. There is no reason as a driver to do anything other than the zigzag path, and yet, with this additional option, with this seemingly superior network, the result is worse for everybody. Everybody's travel times have gone up by a factor of 4/3, from 90 minutes to 120 minutes. What would an altruistic dictator do? Well, it turns out they would be smart enough to just pretend that the teleportation device did not exist. This remains the best thing to do for everybody, even in this new network. Okay? So that's the paradox. The paradox is it seems you can make the network better for everybody, yet the outcome is worse for everybody. Let me convince you that Brace's paradox is not an artifact merely of this model of traffic routing, but rather it's something perhaps a bit more fundamental. Cohen and Horowitz, roughly 20 years ago, pointed out it has some very nice instantiations in physical networks. And this is, I'm going to explain to you now a contraption. This is a contraption you can build. When I teach my courses, I give students extra credit for building these contraptions and uploading the results on YouTube. And they've done it several times. So here's the story. So what you do is it's a contraption made of springs and strings. And you're going to tie them together in a particular way. So you start with some fixed base, like perhaps the top of this desk. And you attach to it, I apologize if this is hard to see. So I'm sure you can see the spring here. In parallel is also a light green string, okay? There's 3 strings. So what you start with one spring, a short string, a second spring. You hang a weight from that initial part of the contraption. That stretches out, of course, the 2 springs and makes the string between them taut. And then you add 2 redundant strings. This one, which goes from the base to the top of the bottom string, and a second redundant string from the bottom of the top string down to the weight. Okay? So this is it. This is what you built. And now the question is, what happens when you take a pair of scissors and you cut this string, taut string, which is presently connecting the 2 springs? Potentially, this contraption will now rearrange itself in some new equilibrium position. The top is fixed, so in this new equilibrium position, this weight conceivably could stay in the same place, or it could become higher, or it could get lower. Intuition might dictate that by severing certain connections, weakening this physical contraption, you'd expect the weight to go further down below because of this weaker contraption. Yet, it turns out, if you run this experiment, the weight will levitate further off of the ground, despite the seemingly weaker physical contraption. There are 2 explanations, if you like. There's a direct one, and there's one which is a reduction to what we've already seen. The direct explanation is that this taut string was forcing the 2 springs to carry the full force of the weight in series. And so each, of course, the length is a function of the force that they are carrying. So that stretches both of the springs out in a quite long way. In severing this string, we free the 2 springs to share the force exerted by the weight. And so each of them is not as stretched out, and as a result, the spring is closer to the fixed base. The other argument would be to notice that the exact same mathematical equations that govern the physical position at equilibrium of this mechanical contraption are the same mathematical equations which govern the traffic pattern at equilibrium in the networks I just showed you. So the correspondence is traffic patterns correspond to force, and the springs correspond to the x links, because the springs are elastic, the length is a function of the force, and the strings correspond to the constants, the 1s and the 0s. And severing the taut string corresponds to removing the teleportation device from Brace's paradox and recovering the superior equilibrium in the original network. Any questions at this point? Okay. So that's a bit of background about how inefficiency arises, not just in the examples that Professor Chazelle discussed, but also in this very natural model of traffic routing, which we've studied for most of the 20th century and since. So we've seen that equilibria of games, in particular routing games, they can be inefficient. We saw this in Pigu's example. We saw this in Brace's paradox. By inefficient, I just mean an altruistic dictator could do better than the equilibrium. I'm going to want to posit an objective function. You don't have to do this, but this is very convenient for this lecture. I'm going to assume for today that a dictator would want to minimize the average travel time of the traffic. You could look at other objective functions, but I will work with the average travel time for today. So what is this mysterious phrase called the price of anarchy? Well, the idea is we're going to try to quantify just how inefficient equilibria are. We know they're not 100% efficient, but maybe we can identify interesting situations, weak conditions, weak assumptions, under which the equilibria are close, within a small percentage of the fully efficient solution, of what we would dictate for society. Okay? So that's the research goal. When is it the case that equilibria are good approximations of optimal solutions? That competition or self-interested decision-making is a good approximation of collective decision-making or centralized optimization. One reason you might care about this from an engineering perspective is if you're thinking about, say, big networks, like the internet or a chunk of the internet, it's very reassuring to know that you don't have to build some sort of complicated centralized control system to optimize things perfectly if you can prove that just letting the users optimize on their own behalf is a reasonably good approximation thereof. So it allows for lighter weights, easier to build, cheaper engineering systems if you have results arguing that the gap is small. So let me just briefly say what the model is. Basically, the model is exactly what you would think it would be, given the examples I've already shown you, if I wanted to allow bigger and more complicated networks. So in the pictures, the networks will always be small and simple, and those are good for intuition. But I will state a couple of theorems, a couple of mathematical results, and for those theorems, the networks can be as big as you like. There can just be any old graph G with some vertices or nodes and some edges connecting the vertices. In all the pictures, there'll be one place where traffic comes from and one place where it goes. For the theorems, the networks can be more complicated. You can have many different places where traffic begins and many different places where traffic is destined to. And there's just some amount of traffic for each origin and each destination. In all of the examples, I've been using simple functions like x and 0 and 1. And those are enough to get interesting phenomena. But sometimes we'll want to allow more general cost functions. A cost function says, as a function of how much traffic is using a given link, a given road, how much travel time does everybody experience? In the simple case, it's going to be a nice linear function, but it can be interesting to think about other functions as well. Okay? I will always, of course, assume that these functions are non-decreasing. The more traffic, only the more travel time. All right? So that's the model. So the price of anarchy is just the ratio in the objective function value, or in our context, the ratio in the average travel time between the result of our two different thought experiments. So on top, we put the result of our first thought experiment, namely, let people do whatever they want, reach an equilibrium, and see what kind of objective function value or what kind of travel time we get. On the denominator, we pretend, for the sake of argument, that we can control what everybody can do, and we ask, how small can we make the travel time? How good can we make the objective function? So this ratio, of course, will always be at least 1. Okay, so letting people do whatever they want can't be strictly better than picking an optimal solution with a dictator. But as we've seen, it can be worse. It can be higher. So this ratio is at least 1, and we want it to be as close to 1 as possible. The closer this ratio is to 1, the more strongly we can argue that self-interested behavior is not very different than what we want anyways. Okay? So this is a definition due to Koutsoupias and Papadimitriou. I know you met Papadimitriou last week. And in both of the examples that we've seen so far, the price of anarchy has been 4/3. So let's review that. Pigu's example is the first one I showed you. And we argued that in the equilibrium, everybody takes the top link, and the average travel time is an hour. So that number is 1 hour for Pigu's example. The other thought experiment, we say, well, what if we could do whatever we want? What if we can dictate actions to people? And the way to make the average travel time as small as possible, in Pigu's example, is to split the traffic 50-50. And if you do that, half of them are an hour, half of them are 30 minutes, or 1/2. So we get an average overall of 3/4. So the denominator would be 3/4 in Pigu's example, so the ratio would be 4/3. If you do that with the second network embraces paradox, after we've installed the teleportation device, you will recall that on the numerator you get a 2. Everybody takes the zigzag path and gets there in 2 hours, whereas in the original network we had an hour and a half. So that was 2/3/2, or 4/3, yet again. I will explain the coincidence of these two 4/3 shortly. Yes. Pigou, oui. Il est français. Is it the same? Is it the same on the left and the right? It's meant, yes. So it is meant to be precisely the same network, but sort of in two different worlds. In the second world, we let people pick their own path. And in the first world, we pick the paths for them. But it's the same paths, the same network, and the same people. It's just where the actions come from is different in the two experiments. Does that make sense? Good. No, good question. So the distance, in some sense, depends on the congestion. So I'm thinking of travel time. So the road is the same, but if there's more cars using it, it will take you longer. And so in that sense, the distance will be different in the two cases. Yeah, good. Other questions? Okay. So, I don't know how you feel, but I feel that, you know, these two examples where the price of anarchy is 4/3 is not that bad. It's not as good as it could be. It's off by 33%. But given that we're just letting people do whatever they want, I could imagine things might have been worse. So actually, they can be quite a bit worse. Let me explain. Here is a tweak, a small modification of Pigou's network. Let me explain the change. It's the same as before exactly, except where we used to have a linear function of x, I'm going to replace it with a nonlinear function, x to the d. D here is some big number, or even just think of it as 10, okay? So let's redo our two thought experiments. It turns out the first one doesn't change at all. The first one where we ask, what would people do in their own self-interest, and what is the result? All of the reasoning is the same. The worst case scenario on top is an hour. The best case scenario on the bottom is an hour. Everybody should, if they're acting in their own best interest, individually, take the top route. And since 1 raised to the d is 1, it still takes everyone an hour. Okay? So the numerator is still 1. What changes is the altruistic dictator can now do much, much better when d is large. Why? Well, suppose the altruistic dictator, instead of rerouting half of the traffic to the bottom, reroutes a small epsilon fraction. Okay? So maybe d is 100 and epsilon is 0.01. So by routing merely epsilon over to the bottom, now everybody on top gets to t very quickly. The travel time on the top link, by definition, is this 1 minus epsilon raised to the d. 1 minus epsilon is less than 1, so if you keep powering it up a lot bigger and bigger, it's going to go to 0. And if d is large, this will be like 0. So this top edge is acting like a teleporter, essentially. There's a few martyrs who are very slow, but they contribute almost nothing to the average. So the average travel time in this red split is approaching 0 as d approaches infinity and epsilon approaches 0. And therefore, the ratio between the two thought experiments is blowing up to infinity as d grows large. Okay? So it is not the case that in every network you might care about, the price of anarchy is only 4/3. It can indeed be much worse. That's fine. You know, a bad example is an opportunity for a theorem. So what we'd like to understand is there are good cases where the price of anarchy is small, close to 1, and there are bad cases where the price of anarchy is very large. Both of these worlds exist. We want an understanding of which is which. Or put differently, how can we be sure that our networks perform well? Are there simple-to-check conditions so that we know the price of anarchy is small, so that routing takes care of itself and we don't have to worry about it? And obviously, we will need some conditions for that conclusion to be true. So what might we hope would be the case? Well, I've shown you 3 examples. So let's be as optimistic as possible, subject to what we know is true in these three examples. Okay? I've shown you two different examples. They're both simple, but one is a little bit more complicated. And these are the ones that have a price of anarchy of 4/3. All right? This is the one that has a really high, large price of anarchy. So what do the good cases have in common? What they have in common is that the cost functions are simple. They're just 1, 0, and x. They're just these simple linear functions. The thing which is different about the bad case is that it has this very nonlinear cost function. So if we're feeling, I would even say naive, but let's say hopeful, you might hope that as long as we have cost functions which are not too nonlinear, then equilibrium routing might be guaranteed to be pretty good. The price of anarchy might be guaranteed to be close to 1. Why is that possibly naive? Well, we're deriving our intuition entirely from networks that have at most 4 nodes, right? Just very toy networks. And it is not at all clear you can make inferences about complicated networks just from playing around with ones that are so small. So the worry is that in large networks, bad things happen even with very simple cost functions. That is what is not clear at this point. Okay? Well, I'm happy to report that this is a case where optimism wins the day. So pretty much the strongest statement you might hope could be true, given what we know, is in fact true. Okay? So I'll build this up in a couple of steps, but here's maybe the easiest one to remember. So let's now assume, okay, so let's think about a network. I'm going to make one assumption, but only one assumption about the network, which is that every edge, it has some cost function, and I insist that the cost function is linear, or affine. Okay, so ax plus b, a and b are both non-negative numbers. And that is the only assumption I make. The network can be as big and complicated as you want. You can have many different vertices that are origins and many that are destinations with traffic crisscrossing each other. I don't care. In any such network, it is the case that if you look at the travel time of the equilibrium flow, I'm also calling it a Nash flow, if you look at the average travel time of self-interested behavior, that can never be larger, not in any network with linear cost functions. It can never be larger than 33% more than the optimal flow, than 4/3 times the average travel time in the optimal flow. Now, we know that we could not have hoped for a better constant right here than 4/3. We already know actually 2 different examples that meet this inequality with equality. In Pigu's example, we calculated the ratio to be 4/3. Brace's paradox as well, we calculated the ratio to be 4/3. And those are, in fact, it turns out, it's a consequence of this theorem, there are no worse networks for the price of anarchy with linear functions than Pigu's example or Brace's paradox. Okay? Now, you might ask, could we say something stronger in some sense? We know we can't make this any smaller. So you might ask, can we make this a weaker assumption? Can we say anything interesting about cost functions that are not linear? And that would be nice, because those do arise in practice sometimes, nonlinear cost functions. Well, remember we had the nonlinear variant of Pigu's example, which says that the fourth, if we want to say something, even about quadratic cost functions, this number has to change. This number has to get bigger. Okay? So that's what we know. So here's what's true. Again, a still more general result is true, which I'll tell you on the next slide. But for now, let's make it more general by one step. Let's say, okay, I will allow you nonlinear cost functions. I will allow you polynomials with non-negative coefficients with some degree bound, a parameter d. You can pick d however you like. As one example, many textbooks on road networks, when they talk about this classical traffic routing model, they suggest d equals 4 is a good model in some cases for delays of road traffic. So that might be a good concrete example, d equals 4. And so the result says that this number does indeed have to go up, but I can tell you exactly how much it has to go up by. And I'm not going to write down a formula. I could write down a formula, but that's not how I'm going to explain it. Rather, here's the appropriate extension of the linear cost function result. I could have phrased this theorem by saying, Pigu's example is everything. Don't bother looking at other networks. And then you do a computation in Pigu's example, and you say, oh, Well, then the answer is 4/3. If Pigu's example is the worst case, then this magic number is 4/3. And that is the sense in which this theorem remains the same for polynomial cost functions, like, say, degree 4 functions. Pick your d, 4, 10, 20, whatever. This Pigu-like network, this variation on Pigu's example this is the theorem, this is not obvious, this is the theorem, this network is the worst one among all networks, no matter how complicated, how many origins and destinations, that have cost functions with polynomials with degree at most d. There is no network with worse ratio than this one. Okay? Now, once you know that, of course, in principle, if you care about what the magic number is, I've given you an algorithm for computing it. I've told you this is the worst network. You just do a little computation on an envelope, and you will get your magic number. So if you care about degree equals 4, you do a computation, and you find that the 4/3, the 1.33, becomes, I think it's 1.89. And in general, the dependence of this constant, of the price of anarchy on the degree, is a little bit sublinear in the degree. Okay? So you get something on the order of 2 for degree 4 polynomials. It gets bigger and bigger and bigger as d goes bigger, gets bigger and bigger and bigger, but we already knew that had to happen. We knew that from our simple nonlinear version of Pigu's example. So these theorems are not about polynomials. They're true in general. You can guess what the generalization is like, but really if you look at any set of cost functions, so maybe if you work in queuing theory, there are delay functions one cares about in queuing theory. You can use those instead. Pick your favorite. It is always the case that the worst case network amongst arbitrarily complex networks looks like Pigu's example. So basically you just have 2 nodes, you have 2 links. On one of the links you put a constant function, and on the other link you put the nastiest function, the steepest function that you have amongst your set. And that is always universally the worst case. It always gives you the biggest ratio. So it reduces searching for a worst case example amongst all networks in the world to searching only over what's the worst function in your set. So it takes away the complexity of the network. All that matters is the complexity of the cost functions. Let me tell you how I explain these results to people who work in the networking industry. Now I'm talking about communication networks, not road networks. So people who manage networks that are taking your data across the world all the time on the internet. So the way I discuss it is as follows. So people who manage communication networks often think about cost functions that look like this. Okay, so there's some capacity. Okay, so there's a maximum amount of traffic that a link can hold, and the delay grows very steeply as you get close to the capacity. So if the link is only 50% full, you go very fast. If the link is 99% full, because there are queuing effects, you have to wait a long, long, long time. Okay? And this is something you may have experienced when you call in for a customer service line, and if it's close to capacity, you might wait for 45 minutes before you talk to a person. It's exactly the same principle. So this is something people in networking think a lot about. And let's suppose that such a network is over-provisioned by a factor of beta. What do I mean? What I mean is suppose that at equilibrium, every link has a little bit of capacity left over. So on every link at equilibrium, you never get further than, let's say, that far out. Say 90%. So that would correspond to beta of 0.1. Okay, you have 10% left over. You're at most 90% full. Then you can plug this into the general theory I just told you about, and out pops, again, you don't have to worry about the network. You just pop it into a formula, and you get the following expression for the price of anarchy. It's a math talk, so I felt I owed you one formula, one obscure formula. So here's your obscure formula for the day to satisfy my contract. So as a function of beta, this tells you how big the price of anarchy is. All right, so what does this mean? So let's stare at this and try to understand it a little bit. So what if beta was like 1? Okay, so being over-provisioned by, let's say, 99 or 99.9%. That means your network is basically totally empty. Nobody's using it at all. Okay, so that's what beta equal to 1 is. So if you plug in beta equal to 1, you get, if you do this computation, you get 1. Okay? So when pretty much nobody's using your network, all of your links, you're right around here, there is no cost of selfish routing whatsoever. And that's a fairly intuitive statement, I hope. Basically, there is no congestion externality if there's no congestion. Okay, so nobody interferes with each other, so there's no problem with selfish routing. What about the other extreme? So what about as beta gets closer and closer to 0? So there's less and less capacity left over. That means some of the links are getting closer and closer to this asymptote, and this function's getting steeper and steeper. Well, as beta goes to 0, this 1 over root beta is blowing up to infinity. Okay? So it says that as your network is approaching all the way up to capacity, as it becomes totally full, selfish routing is really bad. It's really problematic. Your network performance is going to be very poor if it's totally at capacity. What's interesting about this formula is that it allows you to make very tight quantitative reasoning for intermediate values of beta. So if you're actually running a network, you're not going to over-provision it by 99%. You're not going to have just, merely 1% of your resources being used. But maybe, and in fact, telecommunication companies do this, they'll leave 10% on reserve. They'll say, we'll be okay with only 90% link utilization in our network. So that corresponds to a beta of 0.1. And if you plug 0.1 into this formula, trust me that you get something, roughly 2. So what's the bottom line? The bottom line is, as long as you reserve a little bit of your network capacity, say 10%, to keep things from getting flooded over here, that is a sufficient condition, no matter how complicated your network is, that self-interested routing will be almost as good as optimal. Okay? And so this is something really, engineers find very intuitive. I say monitor the performance, monitor how full your links are. If it goes above 90%, add some more capacity. Okay? Get the utilization down below 90% again. This theory guarantees that the routing performance will be almost optimal. Okay?
Demand for the network is limited. Because if you improve the network, most of the time, the traffic will increase.
Yeah.
And then we are always over-provisioning.
I agree. So the question is about how does the demand change? So in the story that I just said, I assumed that the amount of people using your network remains fixed, okay? And clearly, if as you know, it is not. It is growing over time. But it is a fact. So I guess there's two different issues. One would be the question, how long can this last, right? How long can we have the arms race between capacity and demand? Let me just make one point, which is when I talk about the actual telecommunication companies adding capacity, they do it not merely to anticipate future demand growth. They did do it in addition because they had empirically observed performance gains. So the network performance was observed empirically to be superior with extra capacity, and that gave them a second incentive, which caused them to add more than they thought they needed, even conditioned on future growth. But and then I think I'll just set aside the very important question of, down the line, can this continue forever? I mean, it has been happening for decades, but I don't know for how long. It's a good question. Thank you. Other questions? Okay, so I am not going to tell you proofs of these results, but I do want to highlight one technique which is useful for the proofs and also, I think, interesting in its own right. And this technique is using what are called potential functions. So what I'm going to show you on the next couple of slides is the following fact. I'm going to show you that in one of these traffic networks, right, so how should we think about traffic equilibria? What do they do? So intuitively, if you think back to Pigu's example, equilibria seem to be equalizing travel time across all of the routes. Right? So if you have two routes, one is shorter and one is faster, that's not an equilibrium. Sorry, one is slower and one is faster. That is not an equilibrium because people will change from the slower route to the faster route. So at equilibrium, you have this balancing effect where all of the routes have the same amount of travel time. So this is what equilibria seem to be. They seem to be equalizing a lot of parallel routes. In fact, it turns out equilibria are doing a second thing. They're actually solving an optimization problem, a centralized optimization problem. And at first, this should sound sort of crazy, because what is an equilibrium? As Professor Chazelle discussed, it's all about individuals doing the thing best for them. And we have many, many individuals simultaneously making independent decisions what's best for them. But it turns out mathematically, for this model, we can represent this individual decision making, we can represent their actions as if they were getting together and solving a certain optimization problem. And that optimization problem is called the potential function. And I want to tell you exactly what that is on the next slide. But the gist is, the idea is, equilibria in this model accidentally, inadvertently, solve an interesting optimization problem. And this is an old observation, almost as old as the model itself, or it's over 50 years old, Beckman, McGuire, and Winston. Okay, before I write this down and go through this, let me mention something it generalizes that many of you are probably familiar with from electrical networks. So when you study electrical networks, you see this same sort of duality, the fact that electrical current has two different personalities. On the one hand, it's an equilibrium. It's equalizing the voltage drop across all paths between the two terminals in your network. On the other hand, there's Thomson's principle, which says that electrical current is minimizing the dissipated energy over all, in some sense, routings of the current from the two terminals. So it's equalizing voltage drop, it's minimizing energy. It's doing both of those simultaneously. In the same sense, traffic equilibria are equalizing something, namely travel time, and minimizing something else, the potential function. And I want to show you what that generalization of dissipated energy is for these traffic networks. So here's the claim. Okay? So this is going to be a potential function. So the claim is that an equilibria is inadvertently optimizing over all ways of routing the traffic this funny function here. Okay? So I'll explain why on the rest of the slide. Before that, let me just point out, there's one thing we know equilibria are not optimizing. They're not optimizing what we care about, the average travel time. We have many examples that show they fail to optimize that function. But we're going to show that they do optimize a somewhat related function. Okay? And then ultimately, we'll see that the reason, in some sense, that these bounds in the price of anarchy exist, the reason why self-interested routing is not too different than optimal routing is because they optimize the potential function, which is not too different than the cost function that we care about. That's where we're going. All right, so why on earth would these equilibrium traffic routings minimize some kind of crazy function like this one? So what is this? I sum over the edges of the network. Go ahead and think about just Pigu's example. Go ahead and think about a two-node, two-link network. So then we're summing over each of the two edges. F sub e denotes how much traffic is routed on a given edge. And I'm integrating the cost function from 0 up to the amount of traffic. So if this was a constant function, this would just be equal to f sub e. If this was just the identity function x, this would be equal to fe squared over 2. Okay? So I'm just area under the curve of the cost functions. So it's okay if this doesn't make sense. I'll just go through this quickly for those of you for whom these words have meaning. So why should the equilibrium flow coincide with the optimal point, the minimum point for this function, over all ways of routing traffic? Well, the first thing you do is you just look at the first order conditions, like you would in any constrained optimization problem. So you say, well, at the very least, the optimal solution is locally optimal. That is, if I take a little bit of flow off of one path and I reroute it on another path, at the optimal point, that should only make things worse. Now, first order conditions, those translate into some condition on the derivatives of the problem that I'm given, of the function that I'm given. Now, what did I do? I took the integral of the cost functions. So when I do the first order test and I take the derivatives, I just get back the original cost functions. So if you unwind the first order conditions, it exactly says that any two paths between the same origin and destination that are simultaneously in use, they should have exactly the same travel time. Okay? First order conditions imply that used paths should have equal travel time. So that's pretty much exactly like our equilibrium condition for flows. Now, this is only a local optimality argument. It's only about the first order conditions, which in general are necessary and not sufficient. But because cost functions are non-decreasing, remember you put more traffic on a link, travel time only goes up. Because cost functions are non-decreasing, once you integrate, you get a convex function. So this potential function is convex, and the space of all ways of routing traffic is also convex. So these first order conditions are also sufficient in this case. Okay? So that's the high-level argument of why equilibria can be equally well defined or can be characterized as the inadvertent minimizers of this funny function. Okay? Something which is true but which I won't need today is that this actually establishes both the existence of equilibria without resorting to fixed points, and it also shows that they're unique, which is a nice property of this model. Okay, so this is the last technical slide. So let me just mention, again, why did I tell you about potential functions? One, I think they're cool. Two, it shows you sort of on a moral level why theorems of this form might be true, why equilibria might be at all close to optimal solutions. The high-level idea is we wish equilibria minimized the average travel time function. What they do optimize is this other function with the integrals, the potential function. And if those two functions are close, then equilibria travel time should be close to the optimal travel time. Okay? So the precise calculations, so this is one way of computing the average travel time, where I go over each edge of the network, one at a time. On a given edge, I say, well, how much travel time does it take to go just on this link? That's what this means. This asks how much of the traffic endures this travel time at some point in its route. So this gives me the total. If we think about the case where cost functions are linear, this becomes a quadratic function, AF squared plus BF. A and B are the coefficients of the linear cost function. If I instead evaluate the potential function, what equilibria actually do optimize, then instead of multiplying by the amount of traffic, I integrate the cost function. And you'll notice I get exactly the same expression, exactly the same function, with one extra detail, a factor of 1/2 in the leading coefficients. So again, at a high level, this is what we wish equilibria minimized. This is what is by definition optimal. This is what equilibria actually do inadvertently optimize. Once you see this, once you see that equilibria are exactly optimizing the almost correct thing, you've got to believe they're almost correctly optimizing the right objective function. And they are. So from this fact, from the fact that you have a bi-Lipschitz approximation between the potential function and the cost function, you can easily in one line derive a factor of 2. So this is a weaker statement than what I claimed earlier. Earlier I claimed that with linear cost functions, the worst case is exactly 4/3. I'm proving something which is true but weaker, that it's always at most a factor of 2. Okay? So a stronger statement holds. You need a different proof to establish it. You can prove a 4/3. But this should give you accurate intuition about why on earth you should be able to prove these small constant bound performance guarantees for selfish routing when you have control over the cost functions. This slide should give you all the intuition that you need. So I'm out of time, so I'll wrap up just with a few remarks. So one high-level point, which I hope comes through in this lecture, this traffic routing model, Pigou discussed it, as I said, informally back in 1920. It was studied really quite seriously as a mathematical model beginning in the 1950s. And there are hundreds, if not thousands, of papers written about this model. Yet somehow, before computer scientists entered this domain, there were no results on approximation whatsoever. That was just not part of the cultures of the scientific communities that studied this fundamental routing model. And perhaps surprisingly, by looking at this age-old model through the lens of approximation, we could derive new insights about how it behaved. And we could justify well-known engineering rules of thumb, like why do you over-provision networks to make networks perform better? So let me reemphasize that this idea of the price of anarchy by this time has been analyzed successfully, not merely in routing networks, in many other application domains, scheduling, resource allocation, facility location, auctions, and so on. There's a number of surveys. You can look, for example, on my webpage, or you can talk to me afterwards if you want to know more about the other application domains. But at this point, it's a very rich literature. So let me stop there. Merci à vous pour votre attention.